Good afternoon. This is the workshop on using ADQ to improve Aerospike performance with Intel Ethernet 800 series network adapters. My name is Paul Jensen, and I'll be presenting. This workshop was developed in collaboration with my colleague Tibor Szaboky. This workshop is about actually setting up ADQ to get maximum performance. There's a lot of moving parts, and it is a little tricky to go through. So I'm going to divide this talk into the first part. I'm just going to go over, it's really sort of theory and kind of a review of the relevant parts of the networking stack, and then at the end, I will go through the actual Linux commands to configure the card. But those commands can be somewhat mystical, and the goal is really just to provide enough context that if you have to go off script because of the particular features of your deployment, you're not scrambling to figure out what the commands actually do. Some of them are fairly cryptic. So maybe the first thing to say about application device queues is they didn't come out of a vacuum. It's better to think of them as evolutionary. There are a lot of paradigms for accelerating networking that have been around, and application device queues, as manifested in the Ethernet 800 series, lets you go to really extreme levels because networking at 100 gigs is very challenging. It is really not. It's not about just sticking in a faster card and assuming things will actually go faster. They might go faster, but the trick with performance and system tuning in general is knowing when they're as fast as they possibly can be, when you've reached that local maximum. So 100 gigs is very challenging. And some of that's just the system evolution. You have multi-level caches, multiple cores. There are a lot of paths through the system if you're not disciplined. It's like a pinball, moving downward. And so if you're sloppy, you're going to get tail latency. Meaning there's a lot of paths you can take. Some are faster, some are slower. That variance in an application like the Aerospike server is lethal because it's called tail latency, but it translates into a lot of money because if you get into a situation where 20% of your packets are too slow, you might have to double your hardware to cover those stragglers. So that's one thing to keep in mind as we go through all this stuff. There really is no such thing as a bottleneck. Bottlenecks are always relative, and certainly both the system and the applications are competing for the same resources. So that is why when you go to 100 gigs, especially, you incur this fairly formidable complexity. So the network stack and Linux have been kind of co-evolving from the earliest days. And at 100 gigabits, compared to even what was common a few years ago, 10 gigabits, you have an enormous you have enormous increase in packets to process, but you also again that's so you want to leave enough for the application too. There's two approaches for trying to accommodate this, and just in general, one is use the existing host resources more efficiently, and the other is offloading to the 800 series network card. We're going to see both of these approaches with the ADQ. And again, I do want to emphasize the evolutionary aspects. So this has been underway for decades. There were, in the early days, it was things like having the network card do checksums, so the host didn't have to do that. Having more efficient I/O, so you didn't have host cycles wasted, pulling data off the card. And the most important one, though, of offloading the host is going to be in the area of policy, and I think that's where you're going to see ADQ kind of reaching really the state of the art in terms of the sophistication of the policies you can execute and have them execute off the host, and that is a significant savings. I do want to talk about a couple of earlier technologies that you still see in use, but again, you'll see in ADQ they're taken to a new level. One is the Irq Balance Daemon, which just runs on Linux, and it's pretty simple-minded. It doesn't want the system to become bottlenecked because only a few cores are handling the interrupts, so it tries to spread the load around. A more sophisticated technique is receive-side steering, and the cards that implemented this, it was an early instance of having multiple device queues, and that implies two things. That one is the card can buffer requests, so you don't have to generate an interrupt with each one, and the other is that policy part. There's some intelligence in putting packets into queues with RSS. It's pretty much a hash based on endpoint, and the idea is to spread the load around, but also to try to concentrate packets from the same origin into the same device queue. All right, and this is a nice segue into application device queues. So what do they? How have they extended these themes I've been talking about? One of the big ones is rule-based classification, and in the case of ADQ-enabled cards such as the 800 series, that has completely been offloaded onto the card. So all the classification processing is handled by the card with no host intervention when the packet arrives. And that's sort of half the story, though. The other half, and this is, you're going to hear me say tail latency over and over again, is CPU pinning, because once you've got the packets sorted into device queues, they have to be processed on the host, and the idea here is to set up the queues so each queue is serviced by one of the cores on the host, this not only distributes the load, but also as we'll see, it helps you achieve much better usage of the caches, and that helps with the tail latency. So the characteristics of ADQ in general, though, before we move on, with this level of granularity and sophistication in the rules, now you can move beyond dealing with sort of generic network traffic, and you can actually tailor the rules to a particular application. And in this particular case, we're talking about the Aerospike server, which generally would be the only application running on the server. And as I said, it is fully programmable. It is dynamic. You can change the configuration without having to reboot the host. And those rules can even look inside the packets. Aerospike doesn't necessarily need all those capabilities, but for areas, if you're like trying to prioritize video streams, that level of granularity can be very helpful. Okay, we're going to go through a couple of hardware configurations to try to show this in action. This first example is showing a single socket system running one instance of an Aerospike server. It's got multiple cores, and the things to notice here is you have an 800 series card. It's connected through PCIe. It in turn is taking 100 gig traffic off a switch, and this schematic shows that there is actually a device queue that has been set up in one-to-one correspondence with each of the vCPUs on the host. And so the general flow, and in this talk I'm focusing on incoming traffic, really. Packets will come in, the card will classify them, and the packets will accumulate in the queues, and then at some point an interrupt will be generated and we'll talk about those mechanisms. And the key thing is that core 0 is only going to deal with the packets that have accumulated in queue 0, and likewise for the other queues and cores. So that is this is sort of the first step of the divide and conquer. And the key thing here is initially we have code executing in the driver, kernel code, but we are warming up the caches in each of those cores just with the packets, the data associated with the device queue. Okay, this is a little bit more complicated example. This shows a dual socket configuration. There's two things that have changed. One is that this gets into the pinning. Notice now there actually are two separate instances of Aerospike server running on this host, and each of those is configured to be associated with the cores in one socket. So that's one change. The other change is this is a NUMA architecture, non-uniform memory access. So the traffic that is going to socket 1 from the card, that has to make an extra hop because in the NUMA architecture, each socket has its local memory, and it can access the memory on the other sockets, but it has to go over the UPI bus to do that. That's additional latency. So there is a little bit of asymmetry on the initial transfer, but once the data is in, again, now we have the caches associated with each core populated with data coming from its local memory. And this is where the pinning becomes more important, because remember, the initial processing is done by the kernel driver, but the essence of ADQ is extending that so that in the Aerospike server there is actually a thread set up for each for each one of those cores, and the trick is to try to have the Aerospike's service threads aligned with the drivers, so that by the time you come out of the driver and into user land, and you start to access that packet data, it should already be in the caches by the kernel processing, and that really is one of the keys so now you see we have very uniform behavior, and it's low latency because you've got good cache utilization, but the more important point is there's less variance. And you have fewer of those stragglers that take a bad path, that takes longer. The last configuration I'm going to look at very quickly is where you have two cards, dual socket, and you're connecting each card to a PCI bus for the particular socket. So this is very similar to the previous example, except that, well, one, you have a lot more network capacity because you've added the second 800 series card, but secondly, you're keeping traffic off of the UPI bus. So that's a rough summary of sort of the data flows with ADQ. ADQ, as I said, evolved, and it's not operating in a vacuum. I want to talk about two other subsystems that are these are not part of application device queues, but they are crucial to its performance. And again, with networking and Linux, it's always evolutionary. So ADQ is using these pre-existing mechanisms. The first one is the new API, or NAPI. This was developed in the mid-aughts, and it was developed with long before we got to 100 gigs. But with those kinds of data rates, if every packet interrupts the processor, you're going to kill your performance. Interrupts take hundreds of microseconds. There's a lot of context that has to be saved. And so the new API, the insight is, especially if you have a really heavy load, the kind of load that's going to kill your system, you don't really need to do that. Instead, you want to take advantage of the buffering capability of the card and go to polling. And the bet is that when you poll, you'll see a lot of packets in a lot of queues, and you can and then basically you can at that point you can schedule interrupts on the processes where there's data in the queues to be serviced. Now the servicing is still, that's not done by the polling. That's still done by drivers executing in particular cores. But this eliminates a huge, it basically eliminates the order of magnitude fewer interrupts in the best case, because now that when an interrupt service routine is going to be able to pull a lot of packets off at once. So this is important. It's like I said, it started quite a ways. It's been enhanced many times, and the most recent enhancement, starting with the 4.12 kernel, is very pertinent here, which is the new API has a thing called a NAPI ID, which is a way of naming the device queues, and starting with 4.12. Through get-stock-opt, applications can get access to the NAPI ID. So the Aerospike server, when it is setting up its, when it's starting up, it basically can create threads to service to be affinitized to the cores, but then it can use the NAPI ID as kind of the glue to affinitize a particular service thread to the core where the driver has marshaled the data to get that get those warm caches. The other mechanism I want to talk about is busy polling. So this is also a polling mechanism, but this is operating in a different part of the system. This is between the kernel and user land when you're actually waiting for socket data. And if you don't have this enabled, your application will, when it fetches data, it will have to go into the kernel and to get access to that socket data. And the insight here is that instead of having that be kind of demand driven and the application saying, oh yeah, I've got some data, let me go get it. The busy polling is kind of speculatively looking at the driver side data structures to see if there is data ready, and it essentially stages that marshaling up front, and so now when the application is getting socket data, that kernel time essentially has already happened in the background. So again, you get reduced latency. You are burning some CPU to do this, so this is not on by default. We have found empirically 50 milliseconds is a pretty reasonable interval. Okay, before we go to the actual configuration commands, we're sort of done with the overview now. I wanted to quickly recap a benchmark that was done jointly with Intel and Aerospike last fall to try to put some numbers on this. This benchmark was performed mainly by my colleague at Aerospike, Tibor Szaboky, and Ginger Gilsdorf of Intel. And Intel has published these results in a solution brief, which I've got in the references at the end of this talk. It was a dual socket, dual NIC. These are Xeon second gen, also known as Cascade Lake processors, 100 gig connection to the switch on the server, and then there were 6 client processors running. Those were connected to the switch at 40 gigs. Each of those was running 3 instances of the Aerospike benchmark. So 2 instances of the Aerospike server running for each of the cores on the server side, and then being driven by 18 clients distributed across 6 client machines. So these results, first we'll talk about the throughput, and this is in millions of transactions per second. That lower bar is actually pretty respectable. It's 8.6 million transactions. There's certainly a time when that would be cause for great excitement. But notice that the other bar is actually there's almost it's more than a 75% improvement in throughput. So what is the difference here? They are both doing NUMA pinning. They both have 2 instances of the Aerospike server running, but in the example on the left, there is kind of a disconnect between the Aerospike server is creating a thread for each vCPU, and it's affinitizing. Each of those server threads are being affinitized to a particular core. However, it's not the core that is handling that where the driver is servicing the device queues. And so that means that when the Aerospike service thread starts looking at data on the left side, it's pulling them into the cache for the first time. The case on the right is using that NAPI ID as glue to when those service threads start handling data, the driver has previously warmed up the caches, and so that accounts for, in this case, it's pretty substantial, over 15 million transactions per second. Latency is even more. We're going to yet again talk about tail latency. And so this is a histogram where each packet, we're actually keeping track of per packet latency, bucketing them according to time, and you see that in the first case, that blue line, it kind of meanders down to at roughly 600 microseconds. So you've essentially accounted for all the packets. When you have ADQ-enabled, that's the red line. You see it takes a dive much more steeply. So now you're really seeing the tangible benefits of having all the processing lined up and trying to keep data touched by only one core. And so what's called the predictability or P99 number, which is so that's the time at which 99% of the packets have been processed. That goes from 600 microseconds down to 320, and that's more than 45 percent increase in predictability. And again, that it is just excruciating to have to spend a lot of money for a few stragglers. So that graph is what this talk is all about. And now we are actually at the point where we can go through the incantations, and I use that word advisedly, to actually be able to run Aerospike server using the 800 series card with ADQ, all singing, all dancing. The first thing is you need at least a 4.19 kernel. Some of the newer distros, like Ubuntu 20, actually pass that bar. You do need to look at the configuration to you want to look at your kernel config settings, because there are some settings there, and they do need to be set in a particular way. So even if you're at the minimum level, you still may need to have to rebuild your kernel. Once you've done that, there are some housekeeping. These are the things that if you don't do first, you will do later on. This is like putting the Christmas toys without reading the instructions. So these are the things you really want to do. Disable the firewall. If you're on Red Hat or CentOS, make sure SE Linux is disabled. You definitely want to make sure Irq Balance Daemon isn't running, because that'll fight with ADQ. The next two, the scaling governor and the latency performance, this gets into some exotic internal C states of the processors, and these settings are a little less power efficient, but they coming out of some of the C states can add latency. So you're running the system a little hotter in terms of power, but if you're running a 100 gig card and a Aerospike workload, with millions of transactions a second, that system's going to be pretty busy anyway. And then the last thing, LLDP, I'm not going to talk about it. Implements an IEEE standard, but it can interfere with ADQ, and it's not needed by ADQ. So make sure that's off. Once you've got those housekeeping tasks out of the way, the next set of syscontrol, these are more quota things. This is another thing you really don't want to bark your shins on. So make sure that the quotas aren't going to prevent you, that you have accesses for the resources you need to operate at 100 gigabits. Once you've done that, Linux networking has a long history of host-based traffic classification that operate through queuing disciplines. This tool offload basically tells Linux that you are using a network card, that the 800 series card can handle all the traffic classification by itself. And finally, you do want to enable busy polling. The first two on this slide are pretty obvious, but the last one is not. If you have two 800 series cards and you're putting them on the same subnet, you can get some a logical but undesirable behavior having to do with how the traffic gets out to that subnet, and you really want the traffic to sort of be orderly, and the way to do that is to set up routes. So basically, traffic for one card, it all goes in and out of that card and doesn't stray into the other one. This Red Hat website has a good description of how to do this. It's not Red Hat specific. It's a generic mechanism. But if you're going to operate this way, you do want to pay attention to this. Or again, you're going to spend a lot of time pulling your hair out. Okay, and now we are actually another layer of the onion. This is actually configuring ADQ, and first of all, the queuing disciplines you want to select the MQ Prio, which is a queuing discipline that supports multi-queue hardware. So you want to configure that. The syntax is very tortured, and I'm running out of time, but you're actually declaring two traffic classes, and the key is at traffic class 1 you have you're creating again, it's a very obscure syntax, but you're actually creating in this case 56 queues because this system had 56 virtual CPUs. And then you have to the next command. You are actually again. You can sort of figure out what these are doing by looking at what's in the angle brackets. So you see that adding the filter is specifies a network interface. An Aerospike service port, which is the port the client traffic comes in on, and the IP address of that particular 800 series card. So this is essentially how you establish directing traffic to the right device queues. Adaptive interrupt moderation is just a fancy word for saying that you don't want to have a one-to-one correspondence between packets and interrupts. So you want to disable those mechanisms because we've already talked about that. And then finally. This is sort of a pseudocode shell script, but again, look at what's being substituted in the angle brackets. This series of commands is this is where you establish the one-to-one correspondence between the IRQ, which really means device queue. That's the interrupt that's associated with that device queue. And the core that's going to handle it, and at this point, the Linux side is done. Probably a good idea to review what you've set and make sure you're happy with it. That brings us to almost to the end. The Aerospike server, or in this case servers, because we're going to run one instance for each socket. Aerospike has a configuration file, and there are things that have to be set in there. I'm not showing all configurations, but I am showing basically showing what you would do if you were starting up on a dual socket system. So the first thing is in the service clause of the Aerospike configuration file, you want to specify auto pin ADQ. There are several auto pin settings, but and I don't really have time to go into that, but the ADQ is the one that knows to those service threads for the socket associated with each of those service threads, it is going to use the NAPI ID for the affinitization, and that again that's what ties the userland service thread to what's going on in the kernel in the drivers, and then you have Aerospike servers have 4 ports open. These numbers are conventions, but no reason to deviate from them. The last step is we focus on ingress traffic, but egress traffic is it needs to be prioritized, And the way you do that is there are actually many ways to do that in Linux, but there is a control group that you can set a control group for network priorities, and then basically just launching applications in that control group, it'll inherit the network priority. And in this particular example, we are there's two commands because we're running two instances. We're creating the control group, and then what the syntax is actually doing is this control group is being set priority 1, which is so these numbers are a lower number means lower priority, and now we are actually ready to launch the Aerospike servers, and you do that with CG exec, so you can put it in that control group. At this point, you are up and running, and if you have hardware comparable to the benchmark results, those are the kinds of numbers you are seeing. This is the end of my presentation. Unfortunately, I've kind of run over my time, so I don't. What I would like is I will answer the questions. I would encourage people to write their questions. We will make sure they get answered. I've included a couple of links here for further reference, and I hope you've gotten something useful out of this talk. If the one thing to remember is tail latency, that should be burned into your brain. And thank you very much.